Our universe is a vast and ever-changing place. It's a cosmic dance of unimaginable scale, filled with wonders that stretch the limits of our understanding. It's filled with billions of galaxies, each one a sprawling collection of stars, planets, and cosmic dust, all bound together by gravity. Each galaxy contains billions of stars, many of which have their own planetary systems, potentially harboring life. And it's constantly expanding, pushing outward from a single point of origin billions of years ago. This expansion began with the Big Bang, a colossal explosion that set everything in motion. This expansion is a fundamental part of the universe as we know it. It's like a balloon being blown up, with galaxies moving away from each other as space itself stretches. For a long time, scientists believed that this expansion was slowing down. They thought that eventually, the gravitational pull of all the matter in the universe would cause it to stop expanding and start contracting. Gravity, after all, pulls things together. It's the force that keeps our feet on the ground and binds the planets in their orbits around the sun. It seemed logical that the combined gravity of all the matter in the universe would eventually put the brakes on its expansion. This idea was known as the Big Crunch theory. However, in the late 1990s, astronomers made a startling discovery. Using advanced telescopes and observing distant supernovae, they found something unexpected. They found that the universe's expansion wasn't slowing down at all. It was speeding up. This was a groundbreaking revelation that changed our understanding of the cosmos. Something was pushing the universe apart, counteracting the pull of gravity. This force was mysterious and unseen, yet its effects were undeniable. This mysterious force was dubbed dark energy. It remains one of the greatest enigmas in modern astrophysics, driving the accelerated expansion of the universe and challenging our understanding of the fundamental forces of nature. Dark energy is a hypothetical form of energy that permeates all of space. It's invisible and undetectable by current scientific instruments. We can only infer its existence from its effects on the universe's expansion. Think of it like this. Imagine a balloon with dots drawn on it. As you inflate the balloon, the dots move farther apart. The air inside the balloon is like dark energy. You can't see it, but you can see its effects. But what exactly is dark energy? Scientists don't have all the answers yet. Some believe it's a property of space itself, a kind of energy inherent to the vacuum of the cosmos. Others think it might be a new type of field or fluid that we don't yet understand. Regardless of its true nature, dark energy has profound implications for the fate of the universe. Its accelerating expansion means that galaxies are moving farther and farther apart. Over incredibly long timescales, this expansion will have dramatic consequences. Imagine a loaf of raisin bread dough rising in the oven. As the dough expands, the raisins, representing galaxies, move farther apart. This is similar to what's happening in our universe, but on a much grander scale. As dark energy continues to push the universe outward, the space between galaxies will become increasingly vast and empty. This expansion will eventually affect not only the largest structures in the universe, but also the smallest. One possible outcome of this accelerating expansion is known as the Big Rip. In this scenario, dark energy eventually becomes so powerful that it overcomes all other forces in the universe, including gravity and the forces that hold matter together. Imagine a piece of fabric being stretched tighter and tighter. Eventually, the fabric will tear. This is similar to what could happen in a Big Rip scenario. The very fabric of space-time itself could be torn apart. If the Big Rip were to occur, galaxies would be torn apart first. Then stars would be ripped from their galaxies, followed by planets being torn from their stars. Eventually, even atoms themselves would be shredded, leaving behind a universe of scattered particles. Section 5. The heat death, a slow fade to black. Another possible end for the universe is known as the heat death, also sometimes called the Big Freeze. This theory suggests that the universe will continue to expand indefinitely, causing galaxies to drift further apart and the overall temperature to drop. This scenario is less violent than the Big Rip, but no less final. Unlike the Big Rip, where the universe tears itself apart, the heat death is a slow, gradual process. In this scenario, the universe continues to expand and cool over an unimaginable length of time. The energy that once fueled stars and galaxies will dissipate, leaving a cold, dark cosmos. Imagine a cup of hot coffee left on a table. Initially, it is hot and full of energy, much like the early universe. Over time, the coffee will cool down until it reaches room temperature. This is similar to how the universe will lose its heat and energy over billions of years. Similarly, the universe will continue to cool as it expands, eventually reaching a state of maximum entropy. In this state, no more work can be done and the universe will be in thermodynamic equilibrium. In this state of heat death, the universe would be a cold, dark and desolate place. No new stars would form, and existing stars would have long since burned out. Stars would have long since burned out, black holes would have evaporated, and matter itself would have decayed into a diffuse sea of radiation. The universe, once vibrant and full of life, would be reduced to a cold, dark expanse, a slow fade to black. Section 6, The Big Crunch, a universe in reverse. The third major scenario for the end of the universe is the Big Crunch. Unlike the Big Rip and Heat Death, which involve a universe expanding forever, the Big Crunch proposes a universe that eventually reverses course. Imagine a ball thrown into the air. It goes up, slows down, and then falls back down due to gravity. The Big Crunch envisions a similar process for the universe. Eventually, gravity could overcome the expansion, causing the universe to contract. In this scenario, galaxies would start moving closer together and the universe would become hotter and denser. Ultimately, all matter and energy in the universe would collapse into a single, infinitely dense point, much like the singularity from which the Big Bang originated. Section 7. The Leading Theory, a universe in pieces. So, which of these scenarios is most likely? The fate of our universe is a topic that has fascinated scientists and philosophers for centuries. Based on our current understanding of dark energy and the universe's expansion, the Big Rip seems to be the most probable outcome. This theory suggests that the universe will continue to expand at an accelerating rate, eventually tearing apart galaxies, stars, planets, and even atomic particles. However, it's important to emphasize that our understanding of dark energy is still very limited. Dark energy makes up about 68% of the universe, yet we know very little about its true nature. Imagine trying to predict the weather a million years from now. The complexity and unpredictability of weather systems make such long-term forecasts impossible. It's an impossible task because our models and understanding of weather systems are only accurate over much shorter timescales. Similarly, our current models of the universe are based on observations and theories that may evolve with new discoveries. Similarly, predicting the fate of the universe billions of years in the future is incredibly complex. The vastness of time and the unknown variables make it a daunting challenge. New discoveries and advancements in our understanding of physics could significantly alter our predictions about the end of the universe. As we learn more about dark energy, dark matter, and the fundamental forces of nature, our theories will continue to evolve. The Big Crunch, or even other scenarios we haven't yet imagined, are still possibilities. The universe is a vast and mysterious place, and its ultimate fate remains one of the greatest questions in science. Section 8. Conclusion. The Unknowable Future. The end of the universe is a topic that has fascinated scientists, philosophers, and theologians for centuries. While we have some intriguing theories about how it might happen, the ultimate fate of the universe remains one of the greatest mysteries in science. What we do know is that the universe is an awe-inspiring and ever-evolving place. The processes that govern its ultimate fate are still being unraveled. As we continue to explore the cosmos and delve deeper into the nature of dark energy, we may one day have a clearer picture of how our universe's story will end.